Imagine a reality where there isn't just one universe, but rather a sea of universes, each spinning its own separate tale. This is the concept of the multiverse. It's not just a product of science fiction, it's a consequence of theories grounded in rigorous scientific research, such as cosmic inflation. The multiverse model suggests the potential existence of infinite replicas of our own system, each subtly altered by varying outcomes of quantum measurements. Pretty mind-bending, right? In the 1920s, scientists discovered that our universe is expanding as galaxies farther away from us have their light shifted to longer wavelengths. This led to the Big Bang Theory, an explanation for the origin of our universe, supported by evidence such as the cosmic web of galaxies, the background radiation from the early universe, and the ratios of light elements. Yet, the Big Bang Theory only describes the early stages of our universe and doesn't explain why our universe has the specific properties we observe. To grapple with these unanswered questions, scientists propose the theory of cosmic inflation. This theory posits that a large amount of energy, inherent to space itself, caused the universe to undergo an exponential expansion, leading to the uniformity and flatness we observe today. Cosmic inflation solves three major conundrums the Big Bang Theory couldn't grapple with alone: why the universe is so flat, why distant regions of the universe have the same temperature, and why there are no remnants of high-energy particles. But perhaps the most intriguing implication of this theory is... wait for it. Hold your horses. We're getting there, just a little bit more patience. What's up, my amazing and curious folks? Ready to unravel another mystery with us? I'm your host, Cesar Chagas, and with me is our brilliant commentator, Sonia. Hope you've strapped in, because we're ready to dive deep into the enigma of the universe. Remember, subscribe to our channel and hit that bell icon so you won't miss out on our daily deep dives into timeless curiosities.
Hey there, listeners. It's Sonia Guimarães here, ready to embark on yet another journey into the unknown with you all. Let's explore together.
You know, this idea of multiple versions of us existing in different universes reminds me of an event that happened recently. I took part in a virtual reality experience where I had to make a series of decisions that would determine the outcome of the game.
Oh, interesting. Coincidentally, I had a similar experience recently. I was playing this choose-your-own-adventure style video game. Based on the decisions I made, the game progressed in very different ways. It's fascinating to see how one small choice can lead to a totally different result.
Exactly. And that's the very essence of this multiverse concept. There may be a universe where I made different choices in that virtual reality game, and the outcomes are vastly different. It's mind-boggling, isn't it?
Absolutely. It's like we're living in our own choose-your-own-adventure book, but on a much grander scale. It's thought-provoking and a bit surreal.
So, in essence, the Big Bang doesn't explain why our universe is arranged the way it is. It only accounts for the early stages, not the current arrangement. It's like knowing the recipe to a cake, but not understanding why the ingredients interact as they do to create the final product.
But what would be a practical example of these initial conditions that the Big Bang needed to have? Could you break it down for me?
Sure, let's take the fact that the universe had to have been born with density fluctuations of approximately the same magnitude on all scales. Think of it like a sandcastle. The grains of sand are like matter in the universe. Now, if the grains are not evenly distributed, or if there are big clumps in some areas and not in others, your sandcastle won't be stable. Similarly, for the universe to evolve into what we see now, the density of matter had to be evenly distributed, with only tiny fluctuations.
That's a great analogy. And what about the other conditions?
Okay, let's consider the condition that the expansion rate and the total matter and energy density must have balanced almost perfectly at the start of the Big Bang. It's like inflating a balloon. When you blow up a balloon, you have to apply just the right amount of pressure. Too little, and the balloon won't inflate. Too much, and it pops. Similarly, for our universe to expand and form as it has, the expansion rate, or pressure, and the total energy density, or resistance, had to balance perfectly.
I see, it's all coming together now. So our universe is like a perfectly inflated balloon built on a well-structured sandcastle.
So, physicists sought a new approach to resolve the issues the Big Bang couldn't explain. This led to the theory of cosmic inflation, proposing that the universe was initially dominated by a large amount of energy inherent to space itself.
Okay, so if I get it right, it's like the universe was initially filled with this energy, sort of like a balloon filled with hot air?
That's a good way to think about it. The energy filled the universe and triggered an exponential expansion, much like how hot air causes a balloon to inflate.
But how does this relate to the conditions you mentioned earlier that the Big Bang needed to have?
Well, the theory of cosmic inflation suggests that this energy-dominated state set up the initial conditions we observe today. It's like a prequel to the Big Bang.
Fascinating. So the Big Bang wasn't the beginning, so to speak. There was this phase of inflation that preceded it.
Right, and this period of inflation explains why the universe appears flat and why it seems the same in all directions, among other things. So during inflation, the universe behaved very differently than it does today. Picture it like a rapidly inflating balloon, but instead of air filling the balloon, it's energy intrinsic to space itself. This energy was much greater than what we see today, in fact, about 10 to the power of 25 times greater than the current dark energy density.
That's huge. So basically the universe was expanding at an incredibly high rate?
Absolutely. And what is more interesting is that the rate of expansion didn't slow down, unlike what we see in our universe today, where the density of matter and energy decreases as it expands. This is because during inflation, the energy density was tied to space itself, and as space expanded, so did the energy density. This caused what we call exponential expansion. The universe doubled in size in very tiny fractions of a second.
So if I get this right, the inflationary stage was like a rapid-fire expansion, stretching the universe to enormous scales?
Exactly, and this inflationary period did more than just stretch the universe. It solved several key issues that the Big Bang theory couldn't explain on its own. For example, it stretched the universe to a point where it's almost indistinguishable from being flat. It also ensured that the conditions of the universe are uniform across all its visible parts.
That's fascinating. So it essentially set the stage for the universe as we know it.
Precisely. It also created a spectrum of density and temperature fluctuations across the universe. These fluctuations were essential for the formation of galaxies and other structures we see in the universe today. Now, here's where it gets even more interesting. Inflation not only explains the initial conditions of the Big Bang, but also makes new predictions that differ from the non-inflationary Big Bang. These predictions have been confirmed by observations since the 1990s.
So it's like the theory of inflation has brought us to a deeper understanding of the universe by making predictions that were then confirmed by observations.
Exactly. The quantum fluctuations that occurred during cosmic inflation gave rise to the density fluctuations we see in the cosmic microwave background. These fluctuations are essentially the seeds that led to the formation of stars, galaxies, and other large-scale structures in the universe.
That's mind-blowing. But how do we know the amount of inflation that occurred in the past?
Great question. Based on the properties we observe in our universe today, there's a minimum amount of inflation that must have occurred to reproduce what we see. The flatness, the uniformity, and the density fluctuations. This also implies that there are certain conditions that inflation must satisfy to be successful.
So what are those conditions?
Well, one way to model inflation is to imagine it as a ball rolling down a hill. As long as the ball stays on top, we have inflation. But once it rolls down into the valley, inflation ends, and the energy is converted into matter and radiation. The key is that the ball needs to roll slowly for the majority of inflation's duration, only gaining speed when it rolls into the valley.
That's a helpful analogy. So the slow roll of the ball is crucial for the inflationary period to happen?
Absolutely. It's this slow roll that allows the universe to inflate sufficiently, setting the stage for the Big Bang and the universe as we know it. So as long as the top of the hill is sufficiently flat, inflation can work as a viable solution to the beginning of our universe. When cosmic inflation occurs, The energy inherent in space is large. As the ball rolls down into the valley, that energy converts into particles. This provides a mechanism for not only setting up the hot Big Bang, but also for solving the problems associated with it and making new predictions.
It's astounding to think about how much of our understanding of the universe hinges on this idea of inflation. But you know what I find interesting? All this talk about the universe expanding, doubling in size in tiny fractions of a second, makes me think about how big the universe actually is.
That's an excellent point. It's hard to comprehend, but the observable universe is estimated to be about 93 billion light-years in diameter.
Wow, and that's just the observable universe, isn't it? The universe beyond what we can see could be infinitely larger.
Exactly, and this brings us to another fascinating concept, the idea of a multiverse. This stems from the fact that our understanding of the universe isn't purely classical, but quantum in nature, which means that what's actually rolling down the hill during inflation is a quantum probability wave function, capable of taking on various values.
So you're saying that there could be multiple universes, a multiverse, each with different outcomes based on these quantum probabilities.
Yes, that's the idea. But remember, this is still a hypothesis, and while it's fascinating, it's not yet backed by empirical evidence. So if inflation is a quantum field, the field value can spread out over time, with different regions of space realizing different field values. In some regions, inflation swiftly ends as the ball rolls into the valley, converting the field energy into matter and radiation, leading to a hot Big Bang.
This must be how our own cosmic history unfolded, right?
Exactly. But what's fascinating is that in other regions closer to the top, flatter part of the hill, inflation continues for a longer duration. These regions could be considered as outside of the regions where inflation comes to an end swiftly.
It sounds like those regions are just continuing to inflate.
Yes, in these regions, the universe continues to expand exponentially, even as inflation ends elsewhere. This is the concept behind the multiverse theory, that there are potentially numerous disconnected universes, each with a different outcome based on these quantum probabilities.
And this wouldn't just be a few universes, right? We're talking about an astronomical, perhaps even infinite number of universes.
That's the idea. When we work out the mathematics for getting enough inflation before a hot Big Bang ensues, the notion of a multiverse becomes all but inevitable. So the universe that we observe and inhabit may just be one of countless others in this vast multiverse. Of course, this remains in the realm of theory until we can develop technology or methods to test it empirically. So to put it simply, we need the universe to experience enough inflation so that our universe can exist with the properties we observe. In the regions where inflation continues, they keep expanding exponentially and are still growing in size compared to the regions where inflation ends and a hot Big Bang occurs. The interesting thing is that the size disparity continues to increase as time goes on.
So never-ending expansion in some parts and a Big Bang in others, that's quite the contrast.
Yes, and even if there are an infinite number of regions where inflation ends, there's a larger infinity where it persists. The various regions where it ends, the hot Big Bangs occur, are all causally disconnected, separated further by more regions of inflating space.
So these different universes can't collide or interact because they're separated by expanses of still inflating space, right?
Correct. In essence, if each hot Big Bang occurs in a bubble universe, then the bubbles can never collide. What we end up with is an increasing number of disconnected bubbles as time goes on, all separated by an eternally inflating space. This provides the scientific motivation for a multiverse, with no two universes ever colliding.
It's mind-boggling to think about. An infinite number of universes, expanding endlessly, each with its own Big Bang and potentially different laws of physics.
That's what the multiverse theory proposes. We have overwhelming evidence for the hot Big Bang, and the conditions that set up the Big Bang can be explained by cosmic inflation. This inflating space-time puts forth its own set of novel predictions, many of which are confirmed by observation. And one of the non-observable predictions is the existence of countless other universes, each with their own hot Big Bang, comprising what we refer to as a multiverse when considered in totality. Now, it's important to mention, the multiverse theory doesn't necessarily mean that different universes have different laws or fundamental constants, nor does it imply that all possible quantum outcomes occur in some other pocket of the multiverse. And it doesn't necessarily mean that the multiverse is physically real. After all, it's a prediction we can't verify or falsify.
So, it's basically a theoretical construct at this point.
Precisely. But if the theory of inflation holds true, and all our data indicates that it does, and if our universe is quantum in nature, which all evidence suggests that it is, then a multiverse becomes all but inevitable.
Even if it makes some people uncomfortable.
Yes, it's a challenging idea for sure, and some physicists might take liberties with the concept. But until we have a better alternative to inflation, one that can clear the same theoretical hurdles that inflation has already cleared, the multiverse seems to be here to stay. It's a fascinating and bold frontier in our understanding of the cosmos. So what we've been discussing today is the fascinating idea of a multiverse. It's not science fiction, but rather a natural outcome of the theories of cosmic inflation and quantum mechanics. The multiverse suggests that there may be an infinite number of systems, including copies of our own world, with slight variations due to different outcomes of quantum events. While it's a concept that some might find difficult to accept, it is nonetheless grounded in scientific principles.
It's amazing to think that our universe, which we already struggle to comprehend, might just be one of an infinite number. It's like the ultimate expression of there's always something bigger out there. We're living in one of many bubbles, each with its own hot Big Bang, separated by expanding space, in an ever-growing cosmic bubble bath.
And you thought choosing between 31 flavors of ice cream was tough.
Haha, indeed. Thank you so much for joining us today and for taking this journey across the cosmos with us. If you enjoyed the episode, please do hit that like button, leave a comment, and share it with your friends.
Yes, we appreciate your support, and we're excited to hear your thoughts on the multiverse theory. Until our next adventure in the stars, take care and stay curious.
Goodbye, everyone. Stay safe and keep exploring.
This curiosity comes from an article titled, "Why Scientists Think the Multiverse Isn't Just Fiction," penned by Ethan Siegel and published on Big Think on March 6, 2024. The full URL is in the video description if you're interested in exploring this topic further. Now I'm off.